Dear students, welcome to our second lecture on linear regression. And in this lecture, we will focus on the concept of how to find parameters for linear regression. And we will consider the case of both univariate as well as multivariate regression. And we will focus on ordinary least square method in this video. So as we learned in previous lecture that one of the tasks in regression problem is to determine that what are the parameters of the model, and we generally denote this parameter space by beta. Now we want to fit a generalized linear model, and generalized linear model means, like, for example, we consider a two-dimensional example where on x-axis we have temperature and on y-axis we have pressure, and we observe that for certain temperature what is the value of pressure. So our pressure in this case would be y-axis and temperature would be x, and we want to fit a generalized linear model, and in this case parameters would be slope. So we will denote this particular slope by alpha, and this line will also have some intercept. So this intercept, let us say, is beta in this case. Now when I am emphasizing the word generalized linear model, that means I don't want to make this line pass through each and every point, because first of all, under the assumption of linearity in r square space, this is r square space, that is a real two-dimensional space, it is not possible to draw a straight line that passes through each and every point. So I am identifying a generalized linear model with certain slope and intercept, and when I am fitting a generalized linear model, I would be doing some error. So if this is my y1 corresponding to some x1, I will be having some error, let us say that is epsilon 1. Similarly, this would be error epsilon 2 from my fitted model. This would be my error epsilon 3, epsilon 4 up to epsilon n. Now one thing to pay attention here is that I can have different variations of this particular line and say that this is my generalized linear model. For example, one possibility could be I have this as a straight line and say that this is my second option to have a generalized model. So I say that this is my second option, this is my first option, and now I have to select whether one is good or two is good. So I need to optimize, I need some measure against which I am fitting this line to say that one is indeed better than two. Now intuitively we would always be having some errors, e1, e2, e3, e4 up to en, whenever we are trying to fit this generalized linear model or GLM. And you will encounter this word frequently in literature. We call these as generalized linear models. There would be error associated with each y. For each x we have a ground truth of y, and this would be our prediction. This would be our y1 hat from our GLM, and the difference between y1 and our prediction is an error. Now for each point, for each y, or for each x and y, because they are ordered pairs, we can say that error epsilon I is equal to what we have as a ground truth minus what we predict for I. So this is yi minus what is our prediction. Now if this is ground truth, and if we are fitting a generalized linear model with slope alpha, I can write this equation as alpha xi plus some intercept which is beta. So my error at each point would be yi minus alpha xi minus beta. Now if I have n samples over which I am fitting this line or training this particular model, for n samples, I can say that my sum total of an error would be summation I from 1 to n epsilon I, and that would be summation from 1 to n of yi minus alpha xi minus beta. Now you can see that in this case, if point is above the line, we will have positive error. So epsilon 1 will have positive sign, and epsilon n would have negative sign, but errors have to be additive. So rather than dealing with just the magnitude, with the sign as well as magnitude of the error, we either deal with sum total of an error or absolute values of an error, square of an error or absolute value of an error. And in this case we will go with the square of an error, because taking derivatives would be easier, which we will need for optimization. So what we would say is that, let us say that there is some cost. We will say that whatever error that we are encountering is cost of our model, and we have to minimize this particular cost because we want error to be minimum. So we will say that this cost is j from 1 to n epsilon I square, and we will write it as summation 1 to n yi minus alpha xi minus beta square. And now our question is how to determine estimate the value of alpha hat and beta hat. Now we know that if this becomes a problem of an unconstrained optimization, so whatever value minimizes this epsilon square, which we are saying as j, the argmin or the value associated with that particular alpha that minimizes j would be the best estimate of alpha, and we are saying that that is alpha hat. Similarly, beta hat would be whatever value of beta would minimize this value of j or our cost function, that should be the best estimate of beta hat. And from optimization we understand that this is an unconstrained optimization. We have two variables, so we have to solve for two equations. In first case we will differentiate j with respect to alpha and equate it to 0, and in second case we will differentiate j with respect to beta and equate it to 0. So we have two equations and two variables, and we will solve for it. So those who are new to calculus, or it has been a while since you have used calculus, I'll go in step by step, so you don't have to worry. All you have to uh, go through steps, you have to follow the steps and try to do these calculations on your own to get a good understanding. So let us differentiate j with respect to alpha. So we can write this as summation 1 to n. Since it is a square, 2 will come out. We can write yi minus alpha xi minus beta, and then differentiation of this particular term. So differentiation of this term would be with respect to alpha would be minus xi. Since beta does not contain any term of alpha and yi does not contain any term of alpha, they would simply go away, or their derivative with respect to alpha would be 0. So we can write this as 0 is equal to summation I from 1 to n. This 2 would go on the other side and hence it's meaningless. So when we solve it, we get xi yi. I am also taking this minus 1 on the other side, so minus 2 vanishes. Xi yi minus alpha xi square minus beta xi, because this goes away and this goes away, so we end up with this. Now one thing to see here is that we are still having this term of alpha and beta. So we don't know what is the value of beta, we don't know what is the value of alpha. All we have observed are some xi's and some yi's which we have already submitted. So now we will make the use of second equation. So this will be our first equation. So I am putting this in box. This would be very important as we go forward. So second equation would be differentiation of cost function with respect to beta and equating it to 0. What we get is summation I from 1 to n 2 times yi minus alpha xi minus beta times minus 1 equal to 0, because I differentiate this with respect to beta. This will go away, this will go away, and I would only be left with beta. Alright, so if this is clear, and differentiation of beta with respect to beta would be 1, and here minus sign, so that's why it's minus 1. Again I can write this as summation I from 1 to n yi minus alpha would come out summation I from 1 to n xi equal to summation I from 1 to n beta. Now you can clearly see that this still can be written as summation 1 to n yi minus alpha summation I from 1 to n xi. Summing beta n times would simply be n beta, which implies beta is equal to summation I from 1 to n yi divided by n minus alpha summation I from 1 to n xi upon n. Now one interesting thing here is that if you look at sum of y's divided by total number of samples, it's not a very hard thing to guess that that has to be mean of y. Similarly, summation of all xi's divided by n, it has to be mean of x. So this would become y hat minus alpha hat. So this is the estimate of beta, and we will say that this is going to be our equation 2. Now from 1 and 2, here if we substitute beta as y hat minus alpha x hat, in so substituting 2 in 1, we can write this particular expression as minus summation I from 1 to n y hat minus alpha x hat xi plus alpha summation I from 1 to n xi square equal to summation I from 1 to n xi yi. Now what I will do, I will take all the terms of alpha on one side, and another thing to note, now once we expand it, so let me expand it and then I will make that simplification. I can write this as summation I from 1 to n y hat xi minus alpha x hat xi, and here I would have summation I from 1 to n plus alpha summation 1 from n xi square equal to summation I from 1 to n xi yi. Now if I multiply this term by n and divide this term by n, I would be ending up with something interesting. I can write this as minus, since y hat is constant, it can come out, 1 n can stay out, so this would become I from 1 to n xi upon n. Similarly here I can write alpha x bar n and divide by n summation I from 1 to n xi plus alpha summation I from n xi square would be equal to the right hand side, which is xi yi. Now this particular term is again mean of x, and this particular term again is mean of x. So this reduces to minus n y hat x hat minus alpha x hat and other terms remaining as it is 1 upon n xi square. Similarly here you can always do n by n, and we will encounter this term later. So this would be the mean of products of x and y. Now if you separate the terms containing alpha on one side, we get the expression of alpha as summation I from 1 to n xi yi minus n x bar y bar divided by summation I from 1 to n xi square minus n x bar square. We have done nothing, we have just rearranged these terms. And one interesting thing that you note here, if you recall from our time series discussions, we know that if we divide this by n and multiply this by n, the term in the numerator resembles something like expectation of xy, which is the mean of x times y minus expectation of x times expectation of y. If we take this n outside, this numerator resembles something like this, because this would be xi yi upon n and this would be just expectations of x and y, and term in denominator represent the variance of x, and again we have to divide it by n on and multiply by n on both sides. So we end up with variance of n, and these n cancels out here. So basically, can we say that the best estimate of alpha in this case is covariance of xy upon variance of x? And if you recall from our time series discussion, this is very similar to the expression that we derived for some of the auto AR functions, and when we computed their coefficients of AR1 or ARM processes. So this is how we derive the value of alpha, and now we substitute this back into beta, because we knew that this beta is just y hat minus alpha times x hat, and we have already determined this alpha. We can calculate the beta hat. So this is how we deal with a univariate regression. And the reason why we are covering these coefficients is that because once we start using programming language, it is important to understand that when we should use linear regression or when we should not use linear regression. So if two variables are linearly dependent on each other, that is their covariance is not equal to 0 and variance of x is defined, that is where we should go for linear regression. And that's what the name implies, that these two variables are linearly correlated, and hence we can identify what is the relationship between them and try to fit a generalized linear model. Now continuing to our discussion to more realistic scenario, because when it comes to earth systems and data sciences, in most of the cases we would be dealing with multivariate regression. So we will discuss the case with multiple variables. Now in case with multiple variables, let us say we want to predict y as some constant plus beta 1 times variable x1 plus beta 2 variable x2 plus beta times 3 x3 and so on up to beta n xn. So let us say that you want to predict temperature at certain place, and this temperature depends on carbon dioxide concentration, chlorofluorocarbon concentration, ozone concentration, or methane concentration, and we want to determine what are the betas, and this is our intercept, that is what would be the value of temperature if all these concentrations are equal to 0. Now we want to determine what are the values of beta 1 and beta n. So basically we have k, to avoid confusion, I will use k here instead of n. Let us say that we have k coefficients and xk. Now what we will observe in real world, we will observe some values, that is we will have some training data, and let us say that we have n samples. We make observation of n days temperature, and on those n days we measured all these concentrations. So we have n samples to begin with, and hence we can say that y1 would be equal to beta naught plus beta 1 x1 value of x1 on day 1 plus beta 2 value of x2 on day 1 up to beta k value of xk on day 1. So similarly you can write for nth sample, this would be equal to beta naught plus beta 1 value of x1 on day n plus beta 2 x2 on day n and beta k xk on day n. Now you can see that this can be written in a matrix form, and here we will use some basic understanding of matrix algebra. So we can write this as y1, y2, yn, and we can write this as beta naught, beta 1, beta 2, all the way to beta k. And here, or let us write x first, and then we will write beta first, and that would be the question towards end of this video, where I would ask you to write betas first and x later, and see that how this form changes. So what we can do, we can write this as 1, x11, x21, up to xk1, and here this would be all ones, and we generally call this representing bias in the model, and this is different from the bias variance trade-offs. Don't confuse it with, so this is the intercept simply, and here we will have x value of x1 on day n, and this is xkn, and so on. So this particular notation is very important to understand if we are learning any kind of data sciences or machine learning approaches. And now we can write these coefficients as beta naught, beta 1, all the way to beta k. Now you can see that if I multiply this matrix, so the size of this particular matrix is, there are n rows and k columns, and here I have, this is a vector of size k cross 1. So if I multiply it, I will end up with the same expanded form. But when we are fitting a regression model, as we discussed in case of a univariate regression, there would be some error term associated with prediction of y1. So we will add error vector of order n cross 1. So we can write this particular model in compact form. So I'm saying these particular equations with error term added in compact form, as that we want to predict a y vector, and it is the matrix product of x matrix and beta vector, plus there is some error term which is of size n cross 1. Beta is also k cross 1, x is n cross k. So this is a, so we see that since these inner terms match, this matrix multiplication is permissible, hence we are good here. And error can be written as y vector minus x beta. Now what we want to minimize, we want to minimize the error. However, error could be on positive and negative side, so we want to minimize the square of error. That is, we want to minimize e1 square plus e2 square plus e3 square up to en square, or again I varies from 1 to n, summation of error all the way from I, and we want to minimize this. However, now we are dealing with the matrix notation. Now if we see that, if we write this as the product of error transpose times error, that means what we are doing, we are taking e1, e2 up to en and multiplying it with the vector e1 and en. So this would be e1 square plus e2 square plus en square. Hence we would be focusing on the product of transpose of error multiplied by the error itself. So we can write this as E transpose E equal to, we know that E was equal to y vector minus x. I am, for sake of simplicity, I will not write the brackets around x, but we have to remember that x is a vector here, transpose multiply by y minus xb. Now we have to be a little bit careful here and solve this elegantly. We will say that let's take the transpose inside, and if we take this transpose inside, x beta transpose, and we will have y minus xb. If you know that if you have a vector a b transpose, this can be written as b transpose a transpose. So we will write this as y transpose minus beta transpose x transpose and multiplied with y minus x beta. So after expanding, we can write it as yty. Again, we understand that y is vector, so just for sake of simplicity, dropping the arrow, beta transpose x transpose y minus y transpose x beta plus beta transpose x beta. So this looks ridiculously complex, but if you see that we are just doing some linear algebra here. Now we have to pay attention to this particular term. So this is a small trick that is involved here. So if you look at the size of y transpose, so y transpose in this case would be, size of y is n cross 1. So y transpose will have size of 1 cross n. Beta, then we have x. So x has a size of n cross k. So we will multiply it with n cross k. And we have beta. So beta also has size of k cross 1. And by using the property of the distributive and associative properties of matrix multiplication, it really doesn't matter which terms you multiply first. So what we can say here is that since this will, the order would be 1 cross k times k cross 1, or it is equal to 1 cross 1. That means this term is just a scalar. So if we take transpose, so for example 3 is a scalar, and if we take transpose of 3, we will end up with 3. So the transpose of y transpose x beta should be equal to y transpose x beta, which in turn is equal to beta transpose x transpose y. So using this simple result, we can write this equation that I am highlighting here in purple as y transpose y minus 2 times beta transpose x transpose y plus beta transpose x times beta. So this is our equation of ET. And there is beta vector that we have to optimize. Now again, this becomes a simple problem of optimization, that is to identify at what value of beta we would have minimum errors or minimum sum of square of error. We can say that summation, the differentiation of error transpose with respect to beta should be equal to 0, which implies minus 2x transpose y plus 2x transpose x beta is equal to 0, which implies x transpose y equal to x transpose x beta, which implies, now if we have to calculate beta, what we have to do, we have to multiply both sides with the inverse of x transpose x under an assumption that x transpose x is invertible, and we know that for the condition of invertibility, this has to be a square matrix as well as its determinant should not be equal to 0. So we can multiply both sides by x transpose x inverse, x transpose y, x transpose x inverse, x transpose x beta, which implies beta is equal to x transpose x inverse x transpose y, and this is the best estimate of beta vector or beta vector that we get given certain observations of x and y. Now fortunately we don't have to do all this calculus by hand when we go to programming language. However, it is very important to understand that from where this math is coming, what are its limitations, and how to solve the problems of data sciences using pen and paper to get a clarity of concept. Before we go to programming language in video 4, in fact in video 5 we will talk about gradient descent optimization and Bayesian inference of linear regression that will help us in evaluation and modeling.